Hey everyone, and welcome back. This is LACTF, hosted by UCLA. Overall, very fun CTF. Has a very good difficulty curve and lots of fun challenges. In this video, I'll be covering 8 of the web challenges and 4 of the pogn challenges. They should be timestamped below. With that, let's get started. The first web challenge is Terms and Conditions by Applet123. It says, welcome to LACTF 2024. All you have to do is accept the terms and conditions and you get the flag. So if we open the web page, we can see there's this button here that says I accept, but whenever we try to move our cursor over it, the button moves. So if we try to open up the console, it says no consoles allowed. But if we view the page source and we kind of go through, eventually we'll see the button is here. I think there's a bunch of different ways to solve it, but the way I solved it was I found the ID of the button, I go back, I refresh the page, then I do document get element by ID. This one, we make sure we have it, and then you can just click on it. And once you click on it, it says we get the flag. LACTF, that button was definitely not one of the terms. So fun. The next challenge is flaglang by R2Uwu2. It says, do you speak the language of flags? We're given a website and a download file. So this challenge, I think, is a little bit broken. You can cheese it. Basically, you can convert from one country's flag to another country's flag, and they show you how they say hello. And there's a country called Phlagistan. So you can cheese it by just going straight to Phlagistan and it'll give you the flag. This works because it's going to do some comparison with cookies, and since we haven't modified this left side, we don't have a session, and it just happens that the logic works out such that we can just get the cookie from Phlagistan. The way it's supposed to work though, you're supposed to pick one here, and now I have a actual session installed, and so when I go to Phlagistan, it's going to say, oh no, the cookie or your flag, your default flag has an embargo and you're not allowed to go there. The actual way that you're supposed to solve it is in the back. There's this countries.yaml. And so we can see this is where all the countries are loaded from. And there's one called Phlagistan, and it has the flag here, but it's redacted. If you go through, thankfully syntax highlighting is amazing. You might notice that one of the countries has something very strange, and it's kind of a known bug. But here we go. So the ISO for all these countries, this one's like NF, this is MP. The ISO for Norway is NO, but this actually means something in YAML. This is like a falsy value. And so if you go through the code, basically you find out when you try to view it, if the country deny includes the user ISO, it'll say you have an embargo. But with Norway, the user ISO, which will be from the cookie and pass through blah, 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 will instead be like a falsy value, like no or false or something like that, instead of the string. And because of that, it's allowed to go through. And just to kind of reiterate, if we go to the top Phlagistan, it denies conversion from pretty much every country, including the NO country, wherever it is, somewhere in here. NO. But it's the NO string, not the falsy value. And so kind of a cheeky challenge, just like YAML's a little bit weird when it parses NO. But yeah, pretty interesting. The next challenge is Web La Housing Portal by Bertert. It's just going to tell us that it's vulnerable to SQL injection. We're given a website and a download file. The website's pretty simple. Basically, you can type in a bunch of different queries and then find roommate matches. If we look at the backend, we'll see pretty quickly that it is a SQL injection. It's a little Flask app, so we can do that submit request. It's going to copy all the data. It's going to do a little bit of validation, pretty much just some length checks, make sure there's no comment characters in there. And if that passes, then it's going to insert that data into the SQL injection, which is get matching roommates. So for this query, it's going to do select star from users where, and then this is what we get to put in. So we get to select a bunch of key values and it's going to compare them, but there's pretty much no validation done besides a length check. And then from there, it's just going to run the query. If you go through, you'll find out that there is a flag table in here too. So enter into the flags table value LACTF flag. So we have a SQL injection into this users table, and there's also another table called flags, and we need to read from it. And so this pretty much just screams union injection, so we're just going to do a quick union injection, and we should be able to get the flag. So this is what the query looks like. I just copied it out. So the key value can only be 10 characters long, and the value can be 50 characters long. So we just need to make sure that it's somewhat short, but it's really not too hard to do. So like I said, this is the query that it's going to be inserted into, and this is what we control, the swag equals test. So I'm going to do a query, and it's going to be select star from users where 1 is equal to 2, union. And so if you don't remember, union allows you to kind of read from other tables and include it in the query. So I'm going to union it with the results of select. When you do a union, it needs to match like the same data type as the table that you're doing the original query on. And so the flag table only has this flag string. So we kind of need to expand the results from the flag table so that it matches the user table. And so in the user table, the first field is the ID. So instead of passing an ID, I'm just going to pass in a 0. Then I'm going to grab the flag field from the flag table. And then there's some other stuff on the user structure, like, I don't know, name, roommate, and some other stuff. So we just set those all to empty string from flag. And that's it. It's going to go into the query, and then it's going to finish up with limit 25. But we're returning nowhere in the user field is it going to match 1 equals 2. And so it's only going to return the flag results. And then it's going to limit to 25, but there's only 1. Yeah, that was it. So we can run this real quick. Clear. Let's make it big. Python 3, solve.py. And here we go. So it's going to return a bunch of users, but we did the union on the flag table, and we get the results. LACTF use sanitized input. So fun. The next challenge is Web New Housing Portal by R2UU2. So this is the second version of the housing challenge, but this time we're given a site, an admin bot, and a download file. It also hints that the admin bot will be visiting a Sammy. And if you don't know, Sammy is famous for a MySpace worm, which was a XSS. So presumably we're going to be doing a XSS challenge. So if we load it up, we can see there's a login and register. We can register, I'll register an account in a bit because it's part of the exploit. And like I said, there is an admin bot. And so with the admin bot, we get to give it a URL and have it do something, and it's going to run as Sammy. If we go through the code, we'll find out that there's a user called Sammy. So this is what the admin bot is going to run as. And there's a field called deepest darkest secret, which contains the flag. So the Sammy user, which is the admin bot, has a field called deepest darkest secret, which has the flag. If you go through, eventually you find out that there's this app post finder route, and it'll use the deepest darkest secret in an invite. So what's going to happen is when you request to be someone's roommate, you say who you are, and you also say your deepest darkest secret. And so the goal of this challenge is to get an XSS as Sammy, such that Sammy will request to be our roommate, so that Sammy tells us their deepest darkest secret, and we get the flag. So just very standard XSS challenge where the XSS payload is calling this route as the Sammy user. So first thing first, we need to get our XSS payload working correctly. And so this is what I did to get it working. Basically, we're just going to do a fetch call with method post. This is our body. So we're going to request to become roommates with the user SJP, which is Sloppy Joe Pirates, then just some headers, and then we fulfill the promise. So this is our payload. So we need to find an injection point. And to actually execute it, you can put it in like scripts or something. Sometimes scripts don't work when you do like inner HTML, so it's usually easier just to put it in like an image source on air or any of the handlers. So I just copy this, make it flat, change all the quotes so that they're, the outside quotes don't match the inside quotes, and we have a payload. So we need somewhere that we can do the injection. I think, was it safe? Is it this one the safe one? No. Somewhere it does in inner HTML, I think. Index.search. Could be this one. Yeah, so if you pass the Q parameter, it'll load that user, and then it'll inject into the HTML the user's name in an inner HTML. We know this is bad. This is a full sync, so you can do XSS with this. And the user's username is also another sync for an XSS, and it is on the Q page. But anyways, let's. So we know that either the user or the username are valid XSS syncs. So let's just take our payload and let's create an account. So we're going to say our username is SJP, our name, and our deepest darkest secret is just hi. We're going to register. Cool. Now we can go to find roommates. We need to find an XSS injection. Let's search for SJP. When we search for SJP, we can see here's a URL, and we can see this name isn't loading. This is our payload. We can see image source on air fetch, and it should be executed. We get a 404, but we do get a response. If we go to network, let's reload it. We'll see that it is making a post request to the finder with our payload. So our XSS is being executed, although we're executing it on ourselves, and we're requesting to be our own roommate, which doesn't make any sense. But that means this URL works. So if we were to send someone this URL with query SJP, it'll load this XSS and it'll request to be roommates with SJP, which is exactly what we want. So we can take this, we'll send it over to the admin bot. We'll click I'm not a robot. We'll send it. And it says visit successful. So if we go back to home, we can see view invitations. And we can see we had an invitation from Sammy, and their deepest, darkest secret is LACTF, but most of all, you are my hero, which is also another reference to the worm. But fun challenge. The next challenge is Web Pong by R2Uwu2. It says Pong in Mong. We're given a website and a download file. For this challenge, it's just Pong. We can see we're playing. I'm controlling the red ball, the computer's controlling the green ball, and the blue ball is the Pong ball. If we look at the source code, so this is the server code. It's just Node.js. It's communicating the position of the ball and the paddles over WebSockets. And so there's just a bunch of different code. There's the different paddle positions, the velocity of the ball, the velocity of the paddle, a bunch of math functions, and some validation. And at the very end, if the ball is less than 0, that means that the opponent scored on us, and so we lost. If the ball is in between 0 and 100, it means that the game is still in play. And if the ball is greater than 100, it means that we win. And so part of the challenge, though, is if you look, the green paddle is always going to match the position of the ball. So ideally, we shouldn't be able to lose. Fortunately or unfortunately, I kind of cheesed this challenge, unintentionally, I guess. So first thing I was going to do was create a WebSocket client so we could communicate to it. I thought the idea of the challenge was that you can control the paddle velocity. And so I figured that we were just going to wait till the ball is nearby, and then we were just going to like smack the ball really hard. So that way there isn't enough chance for the opponent paddle to react, because the ball will already be like way past the 100-point mark. But it turns out the solution instead is to use not a numbers. So it turns out if you supply, this is what the WebSocket communication looks like. We can actually just open it up. You can go to network. Let's reload. So WebSockets is run. You can go to messages and you can see all the communication. I think 0 means we're receiving, and I think it's the ball position and the opponent paddle. And a 1 means I think it's our paddle position and our paddle velocity. I could have those mixed up. But like I said, I thought we were supposed to do like a big paddle velocity in here, just so that the ball spikes all the way across and we score. But instead, apparently, if you pass 0, 0, 0, 0, at some point, not a number is introduced into the the game state. And once not a number is there, it's kind of insidious. Any operation with not a number becomes not a number, and it happens. I think the not a number is introduced in one of these two lines. When the server receives a message. And what happens is then ball 0 becomes not a number. And is not a number less than 0? No. Is not a number less than 100? No. Therefore, we must have won. And if we look at the flag, so I'll run the solve script real quick. Oh, I already ran the solve script. So if you run the solve script, actually, let me go back to the solve script. I receive a message and then I just send 0, 0, 0, 0. I'm just doing this to test my script. But at the very end, it says, oh my gosh, I guess you won. You're getting better at the flag. LACTF, I suppose you got better. Not a number, not a number, not a number. So I guess this was the solution, just sending zeros. But yeah, fun. The next challenge is JSON Web Token. By R2Uwu2. It says, with all the hype around JWTs, I decided to implement my own JWT to secure my own JSON fan club site. Too bad it's not in Haskell. We're going to a website and a download file. The fact that it says it's too bad it's not in Haskell kind of implies that it's going to have something to do with types, because Haskell is pretty strongly typed. It could also be like functional programming, but most likely it just means types. But we're given a website and a download file. If we look at the website, there's nothing too exciting. You can say, hi, and my age is 11. And we get this JSON for your web token. And I think this is applet. So if we go through the code, we'll see that there's this app.getImage thing. And if we have a role of admin, we get the flag. So somehow we need to be the admin. The token is passed by a cookie. And so there's this code for decoding cookie. So we can go look at that. It's going to do a bunch of like hashing and hexing, and there's some secret that's going to be XORed with the timestamp, and it's going to add our age, and then it's going to verify the hash of that signature with our info, and if all that matches, it's a valid hash. And somewhere in there, there's some user info that contains the age, the name, and the role. So this is a token it doesn't have to be a token forging challenge, but this is a token forging challenge. So the trick to this challenge is kind of like what that hint mentioned, and it's types. So the trick with this is we get to supply a user age when we do the decoding. And the way this is going to work is instead of passing a real age, what we're going to do is we're going to pass in a age of float, not a number. And so when this is float, not a number, it's easiest just to go through the math yourself, but basically if this is not a number, this whole thing becomes not a number because, let me clear this. So if we do float not a number, we have not a number, and if you do float not a number plus 1, it is still not a number. And because of that, we can basically just corrupt all of this so that we don't have to worry about the secret or the timestamp or any of that stuff. And our salted secret is just not a number. And so when it does, it's going to do the check. When we supply a cookie, we have like the cookie value and the signature. When it does that hash, we don't actually have to know the secret because we're just going to be hashing the string not a number, which is, very easy to hash, and it'll match the signature. And so we can say, put whatever we want in the user structure. So easiest if you just do the math yourself, but it's really not too bad. Basically, we're just going to do not a number trickery. And yeah, once we're able to forge our own tokens, so we're just going to say our role is admin and we get the flag. This is what my solve script looked like. I just copied this over so things were happy. I copied over the create token function because it works just fine. So I'm going to create a token. The username is Sloppy Joe Pirates. My age is not a number. So this is where we kind of get that corruption with the signature. They were also kind of hinting at it in the challenge. Like, it's very strange to do secret XOR timestamp plus the user age into the salted secret. Like, why would you include the age and not the name? Like, why would you include the age at all? Just something smells a little funky there. But anyways, so our age is not a number and our role is admin. And so the code that was provided to us will just generate the token for us. And from there, we're just going to send that cookie over to the image request and we should get the flag. So we'll do Python 3 solve.py. And that was it. Your flag is LACTF prevented the denial of service, but at what cost? So fun. The next challenge is Web ctf-wiki by BlueTech. It says, I am such a huge fan of CTF players that I decided to create a wiki with some of my favorites. Hopefully none of them hack it. We're given a website, an admin bot, and a download file. So for this challenge, there's just a little wiki here. You can create and edit CTF teams, and you can pass the admin bot a URL, and obviously it'll visit that URL. As part of the challenge, this description field is just like a very simple XSS. So we have an XSS, but there's a couple things that make this challenge a little bit difficult. First off, so if I do like script alert 1, script, let's create this. We'll call this SJP, 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 SJP. We're going to create this. The XSS doesn't work if we're logged in for two different reasons. But if we open it up in an incognito, we can see it did work. So it only works if there's no session established, which is weird because it redirects from this view to the edit if you're logged in, and the XSS only happens on the view. So we can only do an XSS if we're not logged in, which is a little bit strange. There's some more strange stuff. This is important, which we'll come back to in a second. The other strange thing is there's this content security policy, and the content security policy is only applied if we are not logged in. Sorry, if we are logged in. So it's default source self, image source, star, font source, and then style source. So we do have script source self, which should be interesting, but there wasn't really any obvious attack vectors. And yeah, there's just not too much. Let's see what else. The flag. So it shows where the flag is. There's a route where we can get the flag. Ignore this. Some of these are my comments. We have to make a post request, which will be interesting, which we'll come to later. Then it's going to check the post request of the user. And if the user has the session password equal to the admin password, which we won't know, then we get the flag. And so presumably the admin bot has this admin password. So if the admin bot was to make a post request to this flag endpoint, the response would be the flag. So the reason this challenge is a little bit tricky, though, is we can do an XSS and we could send this XSS to the admin bot, but the admin bot has a session. And so because of that, it's blocked by two things. First off, we don't get our XSS, and second off, there would be CSP, so it wouldn't be able to execute it. But the trick to this challenge was the interplay between same origin policy and the same site cookies LACs. So if you're not familiar with same site, basically it's a cookie protection to kind of prevent CSRF. And the fact that it's set to LACs means that only certain cross-origin requests are allowed to send cookies. Pretty much if it's like a top-level request, meaning like if you type in the URL into the URL bar and you go there, cookies will be sent. But they're not going to be sent to like if you make a background image request or a background fetch request or something like that. Cookies will not be sent. This is an amazing protection that stopped a lot of CSRF attacks and is very cool. So that means, but this is almost useful for us in this like very specific case because we need an XSS when there isn't a session. So if we were to embed the content in an iframe, the cookies would not be sent, which is good. Because the cookies are not sent, that means that the XSS would happen and there would be no CSP. The other browser protection that's important is same origin policy. Basically, every domain, every origin, scheme, host, port is its own little sandbox, and they are allowed to talk to each other, but they're not allowed to really talk to anything else. I mean, obviously, there's a lot of, it's very complex. Like, obviously, you can like request JavaScript from a different origin, blah, blah, blah. But for the most part, everything's its own sandbox. If you are in the sandbox, you can talk and modify other things in the sandbox. And so that is kind of the exploit of the challenge. So even though we don't have cookies when we first go create an iframe to this challenge that we have the admin bot viewing, if we were to open up a new tab, the new tab would have cookies, but because it's the same origin, we can actually modify the contents in that new tab. And so that was pretty much the exploit. This is what it looks like. So we are going to embed this XSS, and we're going to have the admin view it within an iframe. So we're going to have in the XSS, we're going to open a new window, which is just the challenge. Once it's loaded, we are going to change the contents of this page to this inner HTML, which is just form action flag, send a post request. We could do some JavaScript. There's a bunch of different things we could do, but this is just, I had this code already. And then we're going to submit the flag form. So it is going to do a redirect, the cookies are going to be sent, and the content of this page after, once the page loads will just be the flag. So then I print it out and I redirect to this webhook site with the contents of the page. And I just hope that it happens within, 99 milliseconds. Yeah, so we also need to have it embedded in an iframe so that the initial page load, same site lacks cookies are not sent in an iframe. And so because of that, the initial page load will not have the cookies, so we can actually exploit this XSS. So to put everything together, so we have this SJP, what we're going to do is we're going to put that XSS in here. I don't think I need to change anything. Cookies, webhooks, no, looks good to me. We're going to copy this. We need to put this in an iframe, so I'm just going to comment this out. We're going to put this here. Oops. We'll just get rid of this. Too much crap. This is the source, and then we're going to close the iframe. Cool. And then we need to grab this URL. I have an ngrok that's running somewhere. Way too big. I think we're on 80. So then I have down here I have a Python simple server running. So that's just a static directory, and then it's ngrok is running on top of that. And then we're going to go to exploit.html. So this is going to embed that our actual exploit. So this is the URL we'll send to the admin bot. So if remember, since this is going through the iframe, cookies are not sent, so the exploit is happening. This code inside the iframe is opening up a new window, which you might have saw the pop-up was blocked. The exploit was blocked on this browser, but it'll run on the admin bot. It'll load up the new tab that does have the cookies so that then we can request the flag and then we can send it back. We also need a webhook site open so we can collect the flag once it's sent. Yeah, let's send it to the admin bot and see what happens. I think last time I had to send it a couple times because of that 99 millisecond timeout. Doesn't always work. Oh, there we go. Okay, so it just took a couple of tries. Like I said, not the most reliable code, but LACTF can't keep all my favorite CTFers same site. So yeah, fun challenge. The first pwn challenge is pwn applet123. It says blue tick. Can we get applet GPT? Me, no, we have applet GTP at home, applet GTP at home, netcat port. Given a Docker file, the C file, and the binary. Thankfully, C file is included. I feel like this should be mandatory for all CTFs, but I know I'm biased. So we have the print flag function. So this is a ret to win sort of function. There's a bunch of these responses. So the program's going to start, it's going to do some setup, to define some input. It's going to do an unbounded gets. So we already have a buffer overflow, which is interesting. So one thing we should check is the protections. So if we run checksec on it, we'll see that there's no position independent executable. So we know the address of everything. We know the address of the win function. But the problem is we can't just do a trivial buffer overflow because there is a canary. And so we can't clobber that canary. So we keep reading. If the string contains the word I'm, it'll say, hello, string, I'm applet, and it's going to send it string plus 4. So whatever the address is of I'm, it'll add 4 characters. So ideally, if you say I'm Sloppy Joe Pirates, it'll say, hi, Sloppy Joe Pirates. If you say, please give me the flag, it'll consider it. It says no. If it contains by, it'll break, which will then return. And otherwise, it's going to print out a random response. So thankfully, we have a canary leak. So if we think about how this buffer is probably lined up on the stack, it is probably going to be 64 bytes of this buffer here. And then it's going to search for the string I'm. So if we put that at the very end, so let's just assume this buffer is like all the way full, and then I'm. What's after I'm will be the canary, then the RBP, and then the RIP. So what we can do is we can align I'm so that it actually goes, I'm plus 4 is actually the start of the canary. So what will happen is when it does this printf hi s plus 4, that'll be the start of the canary, and it'll just print out the canary for us, which will be great. So it'll print out the canary, then we get to do this whole thing again. And this time, since we know the canary, when we do our buffer overflow, we're just going to clobber all of this. We're going to set the canary since we know it. We don't care about RBP. We'll just set it to some random value, and we'll overwrite RIP with the address of print flag. And we'll get shell. Oh, sorry, we won't get shell. We'll just get the flag. So let's look at the solve script. So this is pwn tools, all very standard stuff. We're loading in the binary. I set some debugging stuff. We're connecting to the remote host. So the very first time, we're going to send a hello, and then 69 A's, and then I'm. And so it happens that I think it was 72 bytes of stuff on the stack. And so right after that is the canary. The canary also starts with a null byte, so you have to do +1. So it's 69 plus 4, which is 73. So that ignores that very first null byte. So after that, we're going to receive till it says hi, and then we're going to receive the 7 bytes of canary. Don't forget the canary starts with a 0, which is just another protection so that you don't get like accidental puts don't accidentally print the canary if people forget to null terminate stuff. But anyways, so now we're going to do our full buffer overflow. We're just going to send over 72 at index 72. So you can use pwn flat for constructing payloads. Basically, we're saying construct a payload such that at byte offset 72, it's 0 plus the canary, and at byte offset 88, it is the symbol for print flag. And then we send that over. So we'll do Python 3, solve.py. It sends it over, and we get the flag. LACTF, so untrue. So, fun. The next challenge is pwn 52 card Monty by Blue Tech. It says 3 card Monty was too easy for me, so I made 52 card Monty. Can you show me the lady? I'm given a netcat port, a C file, the binary, and a Docker file. So thankfully, we're given C code again. Very much appreciated. In the C code, there is a win function. So this is a right to win sort of challenge. The main code exists in this game function. Basically, what's going to happen is we get to peek into this 52 card deck 2 times, and then we have to guess where the queen is. And then no matter what, we get to go on to a leaderboard. As part of this peek, we get to supply an index, and it's going to tell us the value of the card at that index. So it's offsetted from this 52 card array, and it'll just tell us what value is there. And we get to do that twice. And then at the very end, we guess the queen, but we don't actually use this code. And then at the very end, we go into a leaderboard. It's going to read 52 bytes into this name buffer. But if we scroll up, we can see that the name buffer is only 20 bytes. So we have a very obvious buffer overflow. And if we look at the protections, pi is enabled. So there's a win function, but we don't know what the address of the win function is without an info leak. And there's a canary, so we can't do the buffer overflow unless we know what the canary is or if we can jump past the canary somehow. Cool. But thankfully, the trick is, so at index of your first peek, it doesn't do any validation on this. The only validation it does is this modulus, but you can supply a negative number. And when you do negative modulus, as long as it's below or above minus 52 or whatever, it'll still keep the negative number. So we're allowed to access values in negative of where the cards array is defined and see what those values are. And so what we can do is we can see if there's anything interesting. So we can load this up in GDB. We'll go to Monty. We'll run it. Index of your first peek, I'm going to cancel. I'm going to break here just so we can see what the stack looks like. So I'm doing break at game plus 222. We're going to continue, and I'm going to say an index of 5. So now we're back into the game function, and so we can inspect the stack. So if I was to do stack 20, these are all the different card values. One of these is just some random stack thing, some other stuff, but these are all the different card values. So we can do stack 20 minus, let's say, 10. So these are values in minus address. So this is probably where the cards array starts right here. So if we were to access instead cards minus 1, 2, 3, for example, cards minus 3 is this value, and it would print out this value for us. So we would get a leak to game plus 2222, or 222. So we would have a info leak, and from this we could calculate the address of the win function. We also need to find a canary, so we get 2 leaks. The first, we could leak the address of this game function, which would give us the info leak, so we know the address of the win function. We also need to leak the canary with our second run. To see what the canaries look like, you can type in canary. This is pwn debug, by the way. You can type in canary, and you can see what they look like. So it's going to look like OXE93 something. So we can go back up the stack. I think there's one at like 30 or something like that. Yeah, there's a canary here. So somewhere back like 27-ish or something like that, there's also a canary value. So we can then request to read this value, and so that we have both of our leaks. And then from there, it's just a simple buffer overflow. We're just going to overflow that leaderboard thing. We're just going to pass the canary, the win address, And yeah, that should be it. So let's look at the solve script. All standard pwn tool stuff. For our very first peek, we're just going to read back. I think I'm doing that address that I showed, just -3. We're going to get that elf leak. To calculate the leaks, you can use VM map. So we get a leak, whatever that leak was, and we have this here. This is the base of the elf, or this section for the elf. I'm not sure of the right terminology. And so you can subtract those and you know what the difference is. And so that way you can always align the elf address correctly. So we know what the base of the elf address is. And so that way we can calculate the win function. You don't actually have to calculate this. You could just calculate directly the difference between the leaked value and the win address. I just think it's nice to always have the base address, and then you can just reference it from the symbol that you need. But anyways, so that's our first leak. And then our second leak is that -27. This is how we get the canary. So back 27 is the canary value. We say that the lady is at index 0. We don't really care. And now we get to do the buffer overflow into the leaderboard. So it asks us for our name. Again, we're using pwn flat. So at offset OX18, I'm gonna submit the canary. At OX20, I just need, this is gonna be the RBP that's popped off the stack. The frame pointer, I just submit a valid section that is writable. And so elf.bss is just some writable memory segment. And then we submit the win address, OX28, symbols, the win symbol. I do this +1 just for some stack alignment thing. The very first instruction win is like a push RBP, but you need some stack alignment, and I didn't want to add a return statement, so you can just do this as a quick little hack. So certain libc functions require the stack to be aligned, which means the last, if you look at RSP, it needs to end in a 0, not an 8, just because some instructions use like 16 bits or something like that. And so if it's not aligned, one thing you can do is you can find the address of a return address, ret, and so when it's popping off the next function to call, when it's doing return, if it does a ret, it'll move the stack down by another 8 bytes, which is one way. Or if the function has like an obvious pop right at the start, which this one had a pop, it's just like, or sorry, push RBP, that'll also move the stack by 8 values, and so that way the stack is also aligned. Hopefully that made sense. But anyways, we push all those and we should just get shell. Do Python 3, solve.py. And we get the flag, LACTF Monty C Monty do. So fun. The next challenge is pwn sus by Kaifate. It just says sus, we're given a netcat port, a download file, C, the binary, and a Docker file. So the C file is very short. There's not that much into it. There's a function called sus, which doesn't do anything. Then it's going to do some buffering. There's going to be a value. It's going to do a puts. It's going to define a 42-byte buffer. It's going to read into that buffer and then call sus. So we have an unbounded buffer overflow, which is cool. But there's no win function. So we do have to get shell. If we look at the protections, there's no canary. So we can do a buffer overflow. There's no pi. So we can return back to main. So we can call this functions many times. We could jump to any interesting functions, but there is really no interesting functions to jump to. Fun challenge. So most likely we're going to be exploiting libc. So the first thing we need to do is get libc, since it wasn't directly provided, but they did give us a Docker file. So if we look at the Docker file, they're using a red pwn jail. So you can grab the libc from this. It copies the libraries from here. So Debian, SHA, blah, blah, blah. So one way to grab libc out of these is you can do docker run interactive, and we also need a volume mount. So you can do two-way volume mounting, so you can copy files over. So I'm going to do the current working directory. So print working directory, mount it to the child folder within the Docker container, and then run this. So when we run it, we're now in the Docker container. We can go to the child folder, which is here. We can run the dynamic or load dynamic linker or something like that. This prints out all the libraries that are being used. So it is going to use the libc from right here. So we can do an lsla on this, and we can see this is just a generic libc. So we can copy this into our current working directory, and now we can X out, and we see that we have libc. So we have the libc that is being used in the red pwn jail. That was step 1. Step 2, we need a game plan. One thing that this code doesn't have that you usually use when you're going, so we're probably going to start wrapping. We need to start wrapping to leak some libc addresses so that then we can jump and wrap in libc and we can do a system bin shell. If you look at the code, there's a very useful gadget that you need for a lot of these, and that is the pop RDI gadget. And you use pop RDI so that you can like call puts, for example. So we might want to puts out the global offset table entry for one of these libc functions, so that way we have a libc leak. But there is no pop RDI gadget. But that's where the sus function comes in. If we actually look at the code, let me load up Ghidra. So like I said, normally we want control of the RDI gadget. Like if you call puts, you put the address into RDI. So we do want RDI, but there is no pop RDI gadget. But thankfully, when it calls sus, it's actually going to load this value into RDI, and we can see it right here. So it is going to load these two lines. It is going to load some variable, this local 48, which is, I think it was set to the value of 69. It's going to load whatever value this is into RDI for us. So we don't quite have a pop RDI, but as part of our buffer overflow, we can actually set that local variable. So we're going to do the buffer overflow here. It's going to clobber this, and then this value is going to get loaded into RDI. So it's not a pop RDI, but we basically have full control of RDI from this buffer overflow. So what we can do is we're going to put something interesting in here. And then when we do return, we're going to start wrapping. As part of our wrapping code, we're just going to call puts. We don't even have to do anything because as part of our buffer overflow, we're going to set RDI with this sus call for us for free. We're going to call puts, and it's going to print out the string at whatever we pass into RDI. And from there, we'll get a info leak. Then we're going to jump back to the start of the main function. Now that we know where libc is, we can just start wrapping within libc. And from there, we're just going to load up the string for bin shell, and then we're going to call system. So not too bad. To see what the solve script looks like. So all standard stuff, just bone tools, we're connecting. Like I said, on our very first ROP call, all we're going to do is call puts and then return to main so that we can do the whole exploit again. And as part of that, we need to load that RDI, which is going to happen in the call to sus when it loads that variable with 69. We're going to overflow that variable, and it's at offset OAA when you do pwn cyclic. We're going to load in the value for the global offset table entry for puts. So, at this value, it's going to contain the libc function address for puts. And so we're just going to print that out. For these pwn cyclics, basically what you do the very first time you run it is it's going to do a psend line after sus. You send a pwn cyclic. I'll actually just run this real quick. 100, and you can see what the addresses of everything you need are. So if we do a pwn.gdb.attach, let's actually do it this. And then p.interactive. Let's go here. We do make ubuntu 22, python 3, then we do a tmux, python 3 solve. We are running remotely, not locally. We want local. So we're going to finish. So it is currently doing the gets right now. So if we do another finish and we look, this looks very nasty, but let's see how big we can make it. Cool. So if we do a single step, it is loading the stack variable into RX, and now it is loading RX into RDI, and we can see, maybe I'll just print RDI. Actually, let's print a string. We'll print X. Basically, RDI contains some string. I'm going to have to make it smaller again so you can see RDI. Hopefully, it's not too bad. Smaller again. I still can't see it. I'll make it big again. But basically, RDI is up here, and it contains the value OAAA. So we know in our buffer overflow, OAA is where we want to put whatever we want RDI to contain. If you single step again, so it's going to call sus. We don't care about that. So we're doing a single step instruction, single instruction, single instruction, single instruction, single instruction. Now it's going to pop RBP. So if we cared about RBP, it is going to be at the offset QAAA. And if we step again, it's going to pop whatever's on, oops, sorry, wrong one. Now it's going to pop whatever's at return, which is the top of the stack. And so that is address SAAA. Anyways, that is how you get all the indexes that are used for writing the exploit. So we needed SAA was the offset to our return address, and OA was the offset into where we need to put the value that's going to be loaded into RDI. So just a quick way to get all those offsets so you don't have to count hand by hand and put dead beef all over the place. But anyways, we're going to put puts into the RDI. We need a valid stack address just because we're going to be running it over again. So we're going to do elf.bss, and then we put our ROP chain, which is just going to call puts in main. As soon as the ROP call starts, it's going to leak out the global offset table. Do I still have it loaded? Oh, but actually, I'll just run it again. So the global offset table has the value for puts, and it is at this address here. Let me make this bigger. So we're just going to be leaking this value right here so that we have the libc map, or libc leak. Then we calculate the base of libc so that we can start wrapping again. But this time, instead of wrapping within the elf, we're going to wrap in libc so we have all the gadgets we could ever want. We're going to look Again, we're going to have a stack alignment issue where things need to be, the RSP needs to end in a 0, not a 8. When you do this wrapping and you jump directly into a libc function, sometimes this happens. So we're just going to add a random return address from somewhere. And then the next thing we're going to do is we're going to call system on the contents of bin shell. And so pwn tools is magic. It's going to do it for us. It's going to find the address of bin shell for us. And then when we say wrap system, it's going to do the pop RDI with this address for us and call system. So we just do the whole chain again. So we're going to do sus at the offset -8. So this is the RBP that's popped off the stack. Just put in some fake stack pointer and then do the libc wrap code and we should get shell. So let's set everything back. Don't think we need this stuff. See what happens. Close, make it big, Python 3, solve.py. Cool. We got a libc leak, it's running, and we have shell. So cat out the flag, and LACTF amongst us. So fun. The next challenge is Pwn Pizza by Kaifate. It says, yummy, we're given a netcat port, a download C file, binary, and a Docker file. So if we look at the challenge, this is the printf challenge of the CTF, I guess. We're going to be constructing a pizza. While we're building our pizza, we can enter a custom topping, and the custom topping will eventually be printf'd. So once you have something like this, it's pretty much game over because you can read values and you can write values with a printf exploit. There's no obvious win function, so most likely we're going to be jumping to libc or doing something like that to get shell. And yeah, that's pretty much it. Pi was enabled, so we need to find some leaks. Ideally, we need a leak for the main elf, so maybe we'll overwrite a global offset table so that instead of calling printf, it'll call system. So we would need a leak to the main elf, and we also need a leak to libc so that we know the address of system. So the way I solved this, there's probably many ways to solve it, but the way I solved it was I just overwrote the global offset table entry of printf with system, like I said, and one of the toppings at the very end will be bin shell. So instead of calling printf bin shell, it'll call system bin shell. Like I said, first things we need is our leak. Thankfully, it's very easy to get links with printf. You can just specify like %13 $p, and this will leak out the 13th value on the stack. So you can just leak a whole bunch of values until you find some interesting stuff. Like I said, we need both a elf leak and a libc leak, so you can get those. And then from there, we're going to do another printf exploit where you can use the %n key to overwrite a pointer to a variable on the stack. And so using that, we're just going to overwrite the global offset table entries. Thankfully, the %n stuff, it used to be you had to construct it by hand, but now Pwn Tools does it for you, and it's absolute magic. This is what the solve script looks like. We're just going to do standard Pwn Tool stuff. Like I said, first we're going to get our leaks. So we're going to add a bunch of custom toppings. 12 means add custom topping. And our custom topping will be $47 $49 $51 And we grab all of those values out, and we construct our leaks, and we construct the base addresses. And so now it'll print out the base of libc and the base of our elf. And so now we are in a good place to start playing. After this, we say we want to make another pizza. Now we're going to enter in another custom offset. For doing the printf exploits, you need to figure out the offset of where the first positional argument occurs. So if we were to do AAAA, Pwn Tools needs to know what offset this corresponds to. So if I do %6 $p, it needs to, 1, 2, 3, 4, 5, 6, 7, 8. It needs to know what the 6 is so that this 6 references this. And so to do that, you can type in something like this, just a whole bunch of A's, then %p, %p. So this will be 1, 2, 3, 4, 5, 6. And eventually one of these %p's is going to print out all the A's. And so you know it is the 6th positional argument is the start of our payload. And this is what I get when I return it. So we know it's offset 6 because 0, 1, 2, 3, 4, 5, 6. 6 is the start of the A's. Anyways, so now we can construct the format string payload. So at offset, we want to, this is our writes. So we want to replace whatever elf the global offset table entry for printf is with system, and our write size is shorts. So we're going to write that, and it's just going to print out a bunch of stuff to the screen, and using %n and a bunch of magic and very cool stuff, our global offset table entries are going to be updated. And then after that, we're just going to ask it to print bin shell. I just put it twice. This could technically be anything because we already have shell. And then it'll call system bin shell for us. Probably the hardest part, not hard, but most frustrating part of this challenge is, again, they're using a red pwn jail, but this time instead of using Ubuntu, they're using Debian. They're very similar, but for some reason pwn in it just wasn't happy using the libc from this. So I grabbed the libc the same way I grabbed libc from the previous challenge. I just create a Docker file, grab it out. It wasn't happy, so thankfully, if you watch, I have a video on my channel called CTF Tools, and I talk about how you can construct Docker containers for CTF. You might notice I do CTF Ubuntu or make Ubuntu 22 a lot. So I am jumping into a Docker container I created that has all my tools for Ubuntu 22. So I also have one for make Debian. And so this again has all my tools, and what I do every once in a while is if there's a Debian version that's specific for a CTF, I will just rebuild my Debian container that already has all my tools with the correct version so that I know it is using like the exact same system. It's going to have the exact same libc, all that stuff. And so then I can test it in this container and I know that, things are going to align correctly. So I highly recommend doing that if you're having like libc alignment issues. But so I run it in the Debian container. And when I did that, I was able to calculate all the offsets correctly, because you need to calculate like the base of the virtual mapping to the leak you get so that you can correctly calculate this base address. Also, depending, sometimes like Debian and Ubuntu, like these values can be different too, depending on the system for some reason. So just make sure you're running it on the closest system. But yeah, after all that, just a simple printf and it should just work. So Python 3, solve.py. We're going to do all of our printf stuff, and we run ls, and we got shell. So cat flag.text, LACTF golf balls taste great. There was a golf ball topping in the challenge, that's why. But anyways, fun challenge. And that is all the challenges I was able to solve. Very fun CTF, had a good time. I might go back afterwards and try to solve some of the longer ones that I just didn't have time for, because they looked very interesting. There was like a bit flipping one, and there was a heap one, played with for a bit. I saw you can get a double free on the fast spins, but just didn't have time to exploit it. But anyways, thanks for hosting, and I will see you at the next CTF. Cheers.